Hello everyone, let's go ahead and explain experiment 8, which is decomposition of hydrogen peroxide. So in this experiment you're going to observe a decomposing reaction that produces a gas, and our reaction is going to be hydrogen peroxide in the presence of a catalyst producing a water and oxygen. And yes, perform a reaction involving a catalyst, collect gas over water and measure the gas volume. And also we're going to use Dalton's law of partial pressure to calculate the partial pressure of a component in a gas mixture. And also we're going to learn how to use ideal gas law to calculate the number of moles of a gas involved in a chemical reaction. And also we're going to work with the stoichiometry to find out the molar ratios and determine the mass percent of a substance in an aqueous solution. So the reaction that we are going to use is hydrogen peroxide decompose in the presence of potassium iodide catalyst to give us water and oxygen gas. And our goal for this experiment is to find out the mass percent of hydrogen peroxide. That we can find out if you can find out the mass of hydrogen peroxide, you divide it by the mass of the solution times 100. Okay. So how are we going to perform the experiment? This is what we're going to do. Okay, this is how we're going to perform the experiment. Of course, you will be watching the virtual video. It will explain you how the experiment is done. You will see a similar setup like this. You have a Erlenmeyer flask. You're going to take about 5 grams of hydrogen peroxide. You're going to be taking about, you're going to take a graduated cylinder. You're going to put about 5 grams, 5 milliliters. It would be about the same amount, about 5 milliliters of hydrogen peroxide. And then you're going to put into this flask, H2O2. You're going to put it into the flask. And you're also going to put potassium iodide also into the same flask. And then you're going to hook it up through a tube to an inverted water-filled graduated cylinder. Okay, before we start the experiment, you will see this setup being made, that this graduated cylinder over here is completely filled with water, but it is immersed in the water, and we're gonna let the reaction take place with the hydrogen peroxide and potassium iodide. What's going to happen is, let me go ahead and write the equation. H2O2 hydrogen peroxide in the presence of the potassium iodide catalyst, it's going to decompose to water and oxygen gas. Okay, oxygen gas. Now the oxygen gas is going to collect above the water inside the graduated cylinder. So we can find out the volume of the oxygen gas collected by looking at the volume of the empty space. It's not empty, that is oxygen gas going to collect there. As the reaction proceeds, the oxygen gas that form goes through the tube, rubber tube, and collect on top of water inside the graduated cylinder. But in this space here, not only oxygen, you can also have some water vapor, because we are collecting it on water. Okay, and we're going to find out what is the barometric pressure of the atmosphere, and then we can find out the vapor pressure, and from that, using the Dalton's total pressure equation, we can find out the vapor pressure of oxygen. And at the same time, we can find out the volume of oxygen gas collected through this experiment, and then we can find out the temperature of the water. So then we know what is the temperature we collect. So we can find out the basically pressure, we can find out the volume of the water, volume of the oxygen, partial pressure of the oxygen, and then we can find out the temperature. Okay, so we can use the ideal gas law PV equals nRT to find out the number of moles of oxygen collected through this decomposition process. Once we find out the number of moles of oxygen, then we can relate it to the number of moles of hydrogen peroxide because the ratio is 1 to 2. So once you find out the number of moles of hydrogen peroxide, then we can convert it to mass of hydrogen peroxide, and then eventually we can find out the mass percent of hydrogen peroxide in the sample that we got. So that is the experiment we are going to do. Okay, and again please watch the virtual video so you will see how the oxygen gas is being collected through water. It's a beautiful reaction. You should all watch. Okay, and this table gives us the vapor pressure of water at certain temperatures or different temperatures. We need this to find out the partial pressure of oxygen, because since we are collecting oxygen through water, so the total pressure is going to be partial pressure of oxygen plus the partial pressure of the water. So if you know the temperature at which the oxygen gas is collected, if you subtract the partial pressure of water from the total pressure of the total pressure, we can find out the partial pressure of oxygen. We need that. So in our calculations, I'll show you how to use all that information. Okay, so it explains here the amounts that we need to take. Okay. Okay. So the data that we are going to collect is mass of the 10 milliliter graduated cylinder with 5 milliliters of hydrogen peroxide solution. First, you're going to take I'll show you the data, experimental data. Okay, all here. So here's what we're going to be doing. So you will see in your virtual lab, you're going to take a graduated cylinder, and then you're going to add about 5 milliliters of hydrogen peroxide, and you're going to get the mass of that. That's going to be the mass of grad cylinder with 5 milliliters hydrogen peroxide solution, 30.470. And you take the Erlenmeyer flask with a side arm, and then you put it inside here. You put it inside, and then you're going to get the mass of the empty 10 milliliter graduated cylinder after you pour it. So then you know exactly how much hydrogen peroxide went inside the flask. Okay, and then you start collecting the oxygen gas. So you hook this up into a inverted graduated cylinder filled with water, and then you're going to collect the oxygen. You're going to let the reaction take place. So hydrogen peroxide will decompose and oxygen gas will collect underwater, and then the water that generates stays inside the flask. Okay, and then initial gas volume is if there is any gas before we start the experiment, that's going to be initial gas reading. And then the final gas volume is when all the oxygen is being completely collected. So what is the volume of the gas? So that's the final gas volume. And then the temperature of the water, the temperature at which we are collecting our oxygen gas. And then the vapor pressure of water. So we need to find the vapor pressure of the water from the table 8.1. So we'll go ahead and see at 22 degrees what is the vapor pressure. 22 degrees Celsius. 22 degrees Celsius, the vapor pressure of water is 19.8. So we need that 19.8, correct? Yeah. So you will write this down here. (19.8). And then the same temperature, so 19.8. That is the vapor pressure from the table, vapor pressure of water. Okay. And then let's see how we're going to do the calculations. Mass of H2O2 solution used. How do you find out the mass of the hydrogen peroxide used? That's going to be A minus B. That's going to be A minus B. So if you subtract 30.470 minus 30.470 minus 25.636, and that is 4.834. 4.834. Volume of gas collected, that is going to be final gas volume minus the initial gas volume. So D minus C, that would be 40. And then volume of gas collected in liters. So this is milliliters. So that's going to be, you need to H times 10 to the negative 3. That is 40.00 into 10 to the negative 3. Okay. And then the partial pressure of oxygen in tow. How do we find out the partial pressure of oxygen in tow? So Dalton partial pressure is total pressure is going to be pressure total pressure total equals partial pressure of oxygen plus the partial pressure of water. So partial pressure of oxygen going to be then total pressure minus the partial pressure of water. What is the total pressure? This is the total pressure, 759.7 minus the partial pressure of water, which is 19.8. Okay, so 759.7 minus 19.8, 739.9. How do we get this number? That number is barometric pressure. You see here the 759.7 barometric pressure minus vapor pressure of water, F. That's how you find partial pressure of oxygen in tow. Now we need to convert this to ATM. How do you convert it to ATM, atmosphere? You take J and you divide it by 760. J partial pressure divided by 760. So that would be 0.974. 974 0.974 ATM. Okay, and then the temperature in Kelvin. So the temperature is 22. So you add E plus 273. 273 plus 22, 295. 295 Kelvin, right? And then the number of moles of oxygen formed. To find out the number of moles of oxygen formed, we use the ideal gas equation, PV equals nRT. Okay, so we can use PV equals nRT. So what we want to find out the number of moles, so the N would be therefore PV over RT. So where do we have the partial pressure for oxygen? P would be, partial pressure of oxygen is in K. So K times volume of gas collected in liters, that would be I. K times I over R, and then the temperature T, we find in L, R over L, number of moles oxygen formed. So the value K is 0.974 times I is the volume, 40 into 10 to the negative 3, and then you divide by the ideal gas constant 0.0821, and you divide by the temperature, which is 295. That will give you number of moles of oxygen formed, 0.0016. Okay, 0.0016. And then the number of moles of H2O2 consumed. How do we find out the number of moles of oxygen consumed? So we use the equation, that is H2O2, when it decomposes, it forms oxygen and water. So 2 moles of H2O2 give you 1 mole of oxygen, 2 to 1. So then the number of moles of H2O2 would be 2 times M, right? So 2 times M, because it's 1 to 2 ratio. So 0.0016 multiplied by 2, that would be 0.0032 moles. And then the mass of the H2O2 consumed. So this is the number of moles. How would you convert number of moles to grams? Using the molar mass, right? So 0.0032 moles. So 1 mole is the molar mass of hydrogen peroxide, 34.02. So you multiply this number by 34.02. 0.1094. That is the mass of the hydrogen peroxide consumed, 0.1095. And then how do you find the mass percent? You take the value you got from O and you divide it by the mass of H2O2 solution used, which is G. So 0.1095 you divide by 4.834. And then so that you multiply this by 100. So this number O over G times 100. Okay, that's how you get the percentage. And that come to be about 0.022 times 2.2%. Okay, 2.2% is the mass percent for the first solution. And you do the same calculation that I just showed you to find out the trial 2. Okay, so then you get the trial 1 and trial 2. You add the 2 together and you divide by 2 to find out the average mass percent. Okay, that's how you would do the calculations. So for the O, part O is what I have shown over here. Mass of H2O2 consumed. For the number of moles oxygen consumed, M is how, this is how you're going to be doing for the M. PV equals nRT. So N would be K times I, that is M. Okay. And for the second trial, trial 2, you can do the same calculations. You will get a different percentage because for the final volume is 51. So your percentage should be a little bit more than 2.2%. Okay. And then add the 2 together, divide by 2, you can get the average mass percent. So that's how you would do the calculations for experiment 8. Okay then. Bye-bye.